Let's continue on with some more requirements for PV system wiring in Article 690, specifically 690.31. We mentioned already PV wire and type DG cable. These have to be listed. You can see the UL standards there, 4703 for PV wire, 3003 for DG, distributed generation cables. PV wire's been around for a while. DG cable's pretty new. We see those in some applications and expect to see them used more and more. You may never encounter them. It depends on what kind of systems you're working on. Here's a couple of examples. PV wire, you can see that this particular PV wire rated up to 2000 volts, and it is listed to 4703. There's an example of some DG cable. This is for N-phase microinverters, two-conductor cable, jacketed multi-conductor cable, and it is listed as a type DG conductor. The single conductor cables have some specific requirements, and that is that they have to be PV wire or a conductor that's multiple rated as USE2 and RHW2 and also marked as sunlight resistant. The sunlight resistant is critical because that's not necessarily a component of either of those two wire types, so we need all three of those to be on there in order for that to be okay. A lot of people are going to use PV wire, but that is an option as well. Now, when it comes to managing these wires, we have to support and secure them every 24 inches. So this is clear guidance on wire management. We'll talk more detail about wire management in a little bit. It's something that we got to do on our PV arrays, and when I look at the image on the slide here, I like what I see. Sorta. There's one thing I don't particularly love, however. Maybe you see it already. We'll get there in a second. What do we have? We've got our junction box on the back of the module, single conductor cable coming out. There's a wire clip to the frame. That's less than 24 inches. We got a nice loop, another wire clip, and here's the thing I don't love, that connector right in the gap between the modules. What does that do? Well, that exposes that connector to more UV. It exposes it to more direct moisture. Don't love it. I would prefer to see this staggered, the connector tucked up in here or here. It's going to make the loops a little different size. They're not going to look quite as nice, but it's going to be a more reliable installation. Otherwise, I'm liking what I see as far as the wire management goes here. We use things like cable ties. Right? We want to make sure that we're not using the white ones. We use the black ones, or even the ones that are a better material than that, something that's going to last. Replacing cable ties when they fail on the back of a flush-mounted roof array, really tough to do. Not as hard on a ground mount or a pole mount, but still, if we don't have to, let's eliminate that ever from happening by using products that are going to last for the life of the system. So, metal clips, other straps or hangers that are made of materials that are going to last and also protect the wire. They have to be identified for securement and support in outdoor locations. Of course, that's where the PV array is. It's outside. We don't want to use stuff that's going to rust or break down quickly in outside conditions. Now, there's an exception to this wire management requirement of every 24 inches. This applies to what we call large-scale PV. Article 691. It's the next article after 690. Large-scale PV. We'll talk about it elsewhere. You may never work on it. If you do, great. You probably know it if you see it. It's got to be at least 5 megawatts of inverter capacity. So these are larger systems. They're engineered, and there's an exception that says, hey, if the supporting and securing of these single conductor cables is part of an engineered design, it's going to be stamped and sealed by a professional engineer, then that's going to suffice. We don't have to follow this 24-inch requirement. So some flexibility there on our bigger PV systems. Okay, that was single conductor cable. Now let's talk about multi-conductor jacketed cables. Type DG is one of them. 690.31c3 has requirements. If it's part of a listed assembly, think like the trunk cable for a microinverter like we see on the slide here, then follow the instructions. You already knew that. If it's not, if you are, for instance, buying a spool of DG cable and using connectors and following instructions for those connectors and installing it, then there are some additional requirements in 690.31c3 that we have to follow. Install it in a raceway. This would be if it's on or in a building and not on the roof. Okay, so the idea here is, yeah, we can run this stuff in free air on the roof, connecting microinverters, whatever we're connecting on the array. But once we're not on the roof anymore, and we're in or on that building, it's got to go inside a raceway, some kind of conduit to protect it. If it's not in a raceway, and if it's not in a raceway and it's in or on a building, that means what? That means it's on the rooftop, right? Then we're going to have it be marked sunlight resistant if it's outdoors. It's got to be protected or guarded where exposed to physical damage. There's a lot in that, right? As the roof, well, it might be protected from physical damage simply by being on the roof, but what if snow catches it or ice catches it, and then it could be damaged by that? Or maybe it's running between rows of ballasted modules, and someone might be walking up and down that row and step on it. Okay, it's on the roof, but it could still be exposed to physical damage. So that's one where you might want to do what? Yeah, talk to your AHJ and make sure they're going to accept what you consider to be exposed to physical damage and not. Now, this wire's got to be routed so it follows the surface of support structures. That could be racking. We want to secure it. We have to secure it every 6 feet at a minimum, and every 24 inches, within 24 inches of mating connectors or enclosures. So when it comes into an enclosure or it's terminating in some kind of connector that's going to plug into something, got to have it secured within 24 inches of that. Now, if we're not in or on a building and we're not on a rooftop, we're going to be in the ground, right? So if it's going to be buried directly in the earth, not in some kind of raceway, then it's got to be marked direct burial. 690.31c2 has a special allowance for PV systems in regards to cable tray. Cable tray is kind of like what you see on the slide here, used in a lot of different applications, in industrial facilities and in different uses. We use it sometimes, especially on ground-mounted PV systems, as a way to manage and hold all of the string wires that are running along that long row of racking. So we have, in 690.31c2, an exemption from cable tray requirements in Article 392, that'd be 392.10b1. Normally, there is a minimum conductor size. I don't remember what it is off the top of my head. Go ahead and look it up if you feel like it. But the important thing to keep in mind is, hey, if we're using PV wire or DG cable, which we would be doing for our PV source circuits in a system like this, we don't have a size minimum or maximum or any requirement. We can use any size in the cable tray, and it doesn't have to be marked as suitable for use in cable tray. Okay, so we could use PV wire. It has the correct ratings to use it outdoors. It's got the right voltage ratings. Doesn't have to be specifically marked for use in cable tray, which again is another requirement that we would normally have to adhere to when using cable tray under Article 392. We do have to, in this kind of an application with PV systems, support the wire every 12 inches. Often that will be built into the cable tray. You can see each one of these is supporting the wire. They're closer than every 12 inches. We then have to secure it every 4.5 feet. You can see the zip tie in this example, securing that bundle to the cable tray. Need that to happen every 4.5 feet. And some of you have probably already noticed, yeah, this is an older system. The white conductors kind of give it away. We said we can't use white conductors for positive or negative because that indicates a solidly grounded conductor. So this was code-compliant when it was put in, not anymore. Point of this slide is the cable tray. Something to keep in mind when it comes to PV wire and DG cable. We're kind of like the only industry that uses it. It's not something that's used in a lot of other applications. And it's also pretty new. And there's a lot of variability in it. They have non-standard outer diameters. Normally, if you get another type of wire that's in Chapter 3, whatever it is, from different manufacturers, as long as it's the same gauge, it's going to have the same outside diameter. Well, that's not true for PV wire. You could get a 1,000-volt number 12 wire from one company and another company, and they could have very different diameters. The insulations are different constructions. They have the appropriate listings. If they're both PV wire, they meet the requirements. They're just made differently to get there. It's non-standard. Same is true of DG cable. It's going to vary based on the voltage rating and the manufacturer. Neither of them appear in the list of all the other conductors in Table 310 4A. We hit on that one a little bit earlier. It's not a spot where we can go and get information on this particular type of wire. So because of that reason, we also don't have sort of the easy cheat tables in the back of the code book that tell us how many of these wires we could put inside a piece of conduit. Right? Normally we can say, oh, I'm using this size conduit of this type of material with this wire of this size, I can put this many in it. And that's a consideration for heating and also being able to pull wire through there and making sure we have appropriate space. But with PV wire or DG cable, where they all could be different, how can we make a table that covers them all? There isn't one. So we have to calculate our conduit fill using the specifications of the conductor that we actually want to put in there and the allowable fill area of the given conduit, which is in Table 1, Chapter 9 of the National Electrical Code. It's not a hard calculation to do. It's just how much can I put in here? How big is 1? How many does that allow me to do? Those limits that we can hit. And it's going to be specific to the wire because they're non-standard. Why would we do this? I was saying, hey, PV wire. Usually we use it to wire our modules. It's single conductor cable in the air behind the array. Well, the fact of the matter is, on a lot of systems, we are running 1,000 volts or 1,500 volts. There's not a lot of wires currently that are rated at that high a voltage. We're going to see that change. It is changing. But as it stands right now, if I need to run, a high current circuit from a combiner box, maybe a 250 amp circuit to an inverter, and it's 1,000 volts, I may end up putting that PV wire in conduit because there's no other conductor I can get that has the right voltage rating. Or maybe I'm just running wires off a roof, and sometimes I would transition to a wire and run it in conduit because it would be maybe cheaper and smaller. But in this case, I'm running PV wire all the way down, and it's got to go through conduit to make it there. In that case, we would need to do the same thing. How many can we put in that particular size of conduit? So something to keep in mind when you run into that. And while we've got the image up here, let's just take a quick look. What do we got? We've got PV wire, 12, a number 12, or a 12 American wire gauge size wire. The insulation rating is 90 degrees Celsius. That'll be important when we size conductors later. You can see it's a dry and wet location rated, and it's listed to UL as a type PV wire. So good to go there. The only thing I don't see on this one is the voltage rating, but I guarantee you it's just barely off of the image. It's on there for sure. It's probably 1,000 volt, might be higher. When we run DC circuits in or on buildings, we've got to follow the requirements in 690.31d. So inside buildings, we say, okay, 690.31d applies to on or in. What we're talking about right now is in the building, not on it, in it. If they're greater, these circuits, the DC circuits are greater than 30 volts or 8 amps, then they have to be in metal, basically. A metal raceway. Type MC cable, metal clad cable, or other metal enclosures. So greater than 30 volts or 8 amps. That kind of covers a lot of what we're doing. Most modules these days on their own put out more than 8 amps, a lot of them. We do a lot of circuits that are greater than 30 volts. Most of our single modules are greater than 30 volts. So if that DC circuit is inside the building, it's got to be in one of these types of metal enclosures or raceways. As an exception, there often is in some of these cases, if we're using a system that has a listed PV hazard control rating, meaning it is listed to be used as a rapid shutdown means. We'll talk about rapid shutdown elsewhere. This only applies to roof-mounted systems on buildings. Then we can either use non-metallic raceways enclosures that are provided as part of the listed product from the point of penetration to the PV control actuator, the hazard control actuator. This is all rapid shutdown stuff. So I don't want to focus on this too much right now. Just keep in mind that when we talk about a hazard control system, this is a overall listed system that accomplishes rapid shutdown, and it does it in a way that allows us to say, hey, we can use these other listed parts and pieces with it. Other times when we install rapid shutdown, we are putting together different parts and pieces from different manufacturers. In that case, yeah, it's going to have to be in metal, those DC circuits inside the building. Here's a relatively new call out in 690.31f that really applies to ballasted systems. And what it says is that, hey, mounting systems can be used that differ from those allowed in 110.13. So the front of the book tells us how we have to mount and install electrical equipment. And if you follow what's going on in there, it kind of makes it seem like using a ballasted racking system would not be allowed. So here's an example of a ballasted racking system, right? It's not mechanically attached to the roof or the structure of the building. It's held in place with the concrete ballast blocks, some of which you can see here. Okay, so we've started to see that there could be a problem developing with other codes and standards in regards to wind loading and seismic events, and possibly making it so that ballasted arrays all of a sudden may not be permitted, and that could be a big deal because these are very common in a lot of commercial applications. So 690.31f says, yeah, we can do this. We can use other methods, meaning ballasted arrays, but we do have to make sure that we account for expected movement of the array. We want to make sure that our wiring that's connected to this thing that is ballasted in place isn't going to be damaged when there's some movement. Now, what would be expected movement? Well, that's not my area of expertise. These are structural calculations, right? These could be due to wind, seismic forces. I guess they could even be maybe due to vibrations in the building. If there's some amount of expected movement, our wiring system is going to have the flexibility to account for that movement to prevent it from being damaged. So this is kind of esoteric, but it is a big deal nonetheless, because the industry was starting to get backed into a corner in regards to these ballasted systems. Mating connectors is a big deal. The PV industry is a connectorized world. All of our modules, for the most part, come with pre-installed factory plug connectors on them. We see plug connectors on combiner boxes, the DC inputs to inverters, maybe the AC outputs to inverters, certainly things like microinverters, module level power electronics. A lot of stuff gets plugged together. And we've realized over the years that, for one thing, this is an important point because it can lead to some bad failures, and it's also often done wrong. I see this all the time doing inspections where I see connectors either put together wrong, matched up with connectors they don't really mate with, and the problems, as you can imagine, are often going to be result in increased resistance in the circuit. Connectors that don't plug together right. Maybe they let moisture in, which creates corrosion, creates resistance, creates heat. Or maybe the little metal pins inside the connectors that actually make the electrical connection, maybe they don't mate together well, even though the plastic body seems like it clicked into place real well. Well, if they don't fit together well, there's more resistance. Again, more heat. So those are big issues, and we see so many connectors out there that it's something that we need to really have a handle on and be sure that we are doing things right to minimize the hazard and the liability that you might then be exposed to. Mating connectors, first off, they have to be latching or locking. So there's different ways. They have little fins on them or tabs that click together, and then you usually need a tool to open them up. In fact, if they're readily accessible and over 30 volts or DC or 15 volts AC, they have to have a tool. My experience, they almost all do have some kind of little tool you use to open them up. So that's just the way we're doing it, no matter what, readily accessible or not. But here's the big one. If the mating connectors are not of the identical type and brand, they must be listed and identified for intermatability. And this would be laid out in the instructions from the manufacturer. So you can't just take one plug connector and somebody else's plug connector and plug them together. They seem like they work. They seem like they fit. But you don't really know what's going on in there. You don't know the integrity of the seal. You don't know if the metal pins are fitting together correctly. And this is something I see done over and over again. Here's two examples on the slide. These are non-intermatable connectors, different brands, different makes and models. They plug together. And one thing we see in the industry is that there is a sort of a dominant connector manufacturer. There's probably 3 or 4, but there's one in particular. And a lot of companies make knockoffs, and they call it compatible. It may say on your module spec sheet, hey, we're compatible with this other type or types of connectors. But if you dig into it, you're going to find they're not listed for that. They're not listed as intermatable. They basically reverse engineered it and said, hey, we made one that'll plug into this other sort of dominant brand that's out there. So this can be an issue because depending on how well they reverse engineered it, it may actually not mate at all. And we've got problems, as I've described already. So this is a really important one to pay attention to. You're not going to find many connectors right now that are, in fact, listed as intermatable. There's not a whole lot of them out there. I can think of maybe 1 or 2, and I think they may both be cases of the newer version is back compatible, intermatable with our older version that we used to make from the same manufacturer. Otherwise, cross-manufacturer, not so much. We don't have a standardized world out there right now. So the thing you can do is make sure that connector A that you're plugging into connector B are the same make and model. That can be difficult. We don't have control over that all the time. Sometimes people want to say, hey, don't cut module leads off, even if you want to do it because you want to replace it with one that you can plug into the one that came connected to your DC to DC converter or microinverter. You got to work around and work your way through that because this is a code requirement now. It's really always been a requirement because of the way these products were listed. You got to follow their instructions. It didn't say I could plug it into that other one. But now this is really showing that this is has a more high profile to it. And it's something that we need to be aware of and address as an industry. 69033D gives us 3 options for mating connectors that they have to meet. Now, to a large degree, this is going to be, the burden's going to be on the manufacturer here. You still may need to select the right connectors, and as I just talked about, intermatability, that's a huge deal. But here's the 3 general options. It can be rated for interrupting the circuit. What does that mean? That means if I open the plug connect under load, it's not going to be damaged, not going to create a big arc. It's capable of interrupting whatever that rating is. It's going to have a limit, of course. We need to stay within that limit, but if we're using it appropriately, follow the instructions, then it's able to do that. So you may run into some of those. What's much more common would be plug connectors that say, hey, do not disconnect under load or not suitable for current interrupting. It's going to be marked that way, and you're going to have to use a tool to open it. This is basically all of the plug connectors on all of the modules. They're all going to say this because, yeah, maybe it could handle one module, maybe not. But certainly when you put it in series with 10, 12, 20 modules and have a circuit that has high voltage, it's not going to be too happy doing that. We see this all the time. Here's an example. It's not on a module, but it says right here, do not disconnect under load. It's pre-printed on there by the manufacturer, the connector. No matter what you're using it with, well, we'll get to that in a second, it's not rated for interrupting the circuit, But there's a caveat here. It could be part of listed equipment and used in accordance with the instructions, and the microinverter here is a perfect example. It's using these plug connects that are mass-produced, tons of them go onto modules, but here we need to connect a module to the microinverter. Well, you got to dig down into the instructions with the particular device. Often, those plug connects on the DC side, even if they say do not disconnect under load on it, if you read the instructions, it'll say, yeah, these are suitable for breaking the circuit under load. It's listed and tested that way. Maybe, maybe not. It depends on the particular device, as I said. But don't be surprised to see that. It happens all the time. They say you can't, but the instructions, because it's part of the listed product that came, that wiring harness there that plugs into the micro and into the module, that's a listed device. And so if we're following the instructions and it says you can, then hey, I can use that as a DC disconnect. The same would be true maybe on the AC output, the trunk cable. May be able to open it under load, maybe not. It all depends. We're going to look to the instructions for clarity on that. There's an informational note here, and that's really kind of building up to what I would say. Some equipment is evaluated to use them as disconnects, even if it says you can't on the device itself, right? On the plug connector. That's what that white writing is right there. Do not disconnect under load. So again, follow the instructions. This is probably something you're most likely to see in terms of connections to module level power electronics. Been talking about microinverters, DC to DC converters. Same thing very well may be true there as well. Finally, 69034, we're moving out of 69031, but just wanted to bring this up, access to boxes. Junction boxes located behind modules, you got to be able to get at them, but they don't have to be accessible all the time. I can move a module as long as there are a way to do that. There's some removable fasteners there, of course, and the wiring connected to the module is flexible enough that I'm not going to yank it out of there when I move it. Obviously, we don't want to damage the thing to do it, so that wouldn't be very practical. So this is something that happens all the time on roof-mounted systems. And it's also something that kind of differs from a lot of other people's just expectation of what the National Electrical Code makes you do. In general, we're not allowed to, I'm making air quotes, bury boxes, make them so you can't just get right at them. But here we're allowed to. It helps with the aesthetics of an array. Put it behind the array. It makes it a cleaner installation. So here's some examples. We've got a pass-through box here. Here's another one. This is the enclosure that's on this system with the microinverters. As long as the wiring running into it is flexible enough and I can remove this module if it has top-down clips on it, for instance, pull it out of the way, get at the box, we're good to go, allowed by 69034. Okay, next we'll talk wire management, big part of PV installation, important detail we need to pay attention to. Catch you there.